Learning Outcome 2.5, Finding the Impulse Response from Discrete Time Difference Equations. You're given a system where the input is x and the output is y. The system is defined by h, the impulse response. The question is, if we know the relationship between x and y, what is h? Remember that h of n is the impulse response. That means that the input is an impulse. Therefore, the output is a response to the impulse or the impulse response. The most common equation relating the input and the output of a discrete time system is an input-output difference equation. You saw these in Chapter 1. An example would be y of n equals x of n plus 2x of n minus 1. And here's another example. Y of n plus 2y of n minus 1 equals x of n. So let's take this first example and determine what is the impulse response. Recall that we're going to set the input to an impulse so that the output will be the impulse response. For this problem, that just means making some substitutions. We said that y was h and x was delta. Therefore, 2x of n minus 1 will be 2 delta of n minus 1. We're done. We know what h of n is in terms of other functions whose values we know. Pause the video and sketch this h. Here's the answer. Let's try another example. A little bit more complicated, same idea. What is h? Pause the video and calculate this. Once you finish your calculations, sketch h. Remember that you're going to substitute x of n is delta of n, y of n is h of n. We make those substitutions, we get this. We're already at the answer for this particular problem. And here's a sketch. Another example. This is more complicated. We still want to find the same thing. We want to find h of n. We're still going to use the fact that x is delta of n and y of n is h of n. Now when we make the substitution, using the same method, we get this equation. However, when we solve for h of n, we don't get something quite as simple as we did before. We still get a delta of n on the right-hand side, but now there's another h on the right-hand side too. So we're not done because we don't know what h of n minus 1 is. We do know that delta of n takes on a value of 1 times 0. So let's think this through a little bit further. If we know that h of n is delta of n minus 2h of n minus 1, we can make the substitution n equals n minus 1. That n becomes n minus 1. That n becomes n minus 1. That n becomes n minus 1. And therefore, this term simplifies to n minus 2. We now know what h of n is in terms of delta of n minus 1 and h of n minus 2. We can substitute this h of n minus 1 into this first equation. Do some algebra. Going fine, h, delta, delta. But now we need to know what h of n minus 2 is. We can again do a substitution. Substitute in, do some algebra. More algebra. H, delta, delta, delta. Now we need to h of n minus 3. How long is this going to continue? Forever. That's right. And if we keep working our way through there, you'll see a pattern, and the answer is that h of n is negative 2 to the n minus 1 u of n. The u of n, remember, turns our functions on and off, and we're going to turn it on at time 0. Okay, this works fine if we only have a first-order system. If we have a second order system, this method will not work nearly as simply because the number of h terms on the right-hand side will keep growing. Every time you substitute 1 in, you get 2 in response, and therefore the number of unknown variables increases. So there's another approach to this problem. Recall that we're saying that if our input is our impulse function, our output is our impulse response. What happens at the very beginning of time when n is negative infinity? We're looking at the impulse response to an impulse, and this has a non-zero value first when n is 0. So all the way back to negative infinity, unless we have a very acausal system, there's never been any input. So we know that there's therefore no output, and we know that our impulse response at time negative infinity is 0. This is called the initial rest condition. So let's see how we can apply this. If we know that h of negative infinity is 0, again we make the substitution of our y of n's, our h of n's, and therefore our y of n minus 1 is h of n minus 1, and our x is delta of n. We're going to look at what happens when n is negative infinity. We know that h of negative infinity is 0. So let's see what happens at the next instance in time, h of negative infinity plus 1. Substituting in n is negative infinity plus 1, we get that h of negative infinity plus 1 is delta of negative infinity plus 1, minus 2 h of negative infinity plus 1 minus 1. A little bit of algebra, that's our h of negative infinity. We know what its value is. And we know that delta of n only takes on non-zero values when the argument is 0. So at time negative infinity plus 1, that argument is not 0. So we know that delta of negative infinity plus 1 is 0. Therefore, at time n is negative infinity plus 1, our delta function is 0, and h of negative infinity is 0. Therefore, h of negative infinity plus 1 is 0. Let's look at the next instance in time, time negative infinity plus 2. Again, substituting in, we got our delta of negative infinity plus 2, h of negative infinity plus 2 minus 1. We need to know the values of delta of negative infinity plus 2 and the value of h of negative infinity plus 1. This will again be 0, and this we determined in the previous step was 0. Therefore, our value at time negative infinity plus 2 is 0. Now, there's an awful lot of this boring zeros going on, but you need to understand the idea. If we really speed forward in time to the time when n is negative 3, we then get delta of negative 3 minus 2h of negative 3 minus 1, which is delta of negative 3 minus 2h of negative 4. Delta of negative 3 is likewise 0. h of negative 4 followed the same sequence and was also 0. Let's do a few more of those. This is just a recap. I've rewritten things so I have more board space. At time n equals negative 2, delta of negative 2 minus 2h of negative 3, again 0. Again, previously we said it was 0. When n is negative 1, delta of negative 1 is 0. h negative 2 in the previous line was 0. When n is 0, delta of 0 minus 2h of negative 1. Oh, look! Delta of 0. Remember the definition of our impulse. When the argument is 0, delta is 1. Suddenly, we have some non-zero values. h of negative 1 from the previous line was 0. Therefore, h of 0 is 1 minus 2 times 0, or 1. Again, just a recap. Let's keep moving forward now. h of 1 is delta of 1 minus 2h of 0. While delta of 0 was 1, delta of 1 will again be 0. And previously, our h of negative 1 was 0, but now we've got h of 0, and h of 0 we just said was 1. So now our output is 0 minus 2 times 1, or negative 2. Next step forward, h of 2 is delta of 2 minus 2h of 1. What's delta of 2? What's h of 1? Therefore, h of 2 is 4. We can graph what our h of n looks like. This process will keep continuing. I will usually tell you how many non-zero terms to calculate. I will not make you solve for the entire function, but you should be able to calculate 3, 4, 5 terms relatively quickly using this method. Let's review the steps. Rewrite the equation in terms of h of n and delta of n. That's just substituting that y of n is h of n and x of n is delta of n. Solve for the latest h of n minus n naught. You don't know what this n naught value is. It might be 0, might be 1, might be negative 1. Whatever has the latest value in time. Apply the initial rest condition. H of negative infinity is 0. And everything before negative infinity was also 0. Write a few steps out just so you know where you're going, and determine where the first n value would be, where the input, any of our x's, any of our deltas, have an argument where the argument is 0, therefore the value of our deltas will be non-zero. And then iterate finding h of n for all subsequent n's. Here you need to work out step by step by step. It's optional to write h of n in a general form. Sometimes it will be pretty obvious what it would be. Sometimes it's a little bit more tricky. If it is obvious, I'll ask you to write it out, come up with an equation for it. If it's not obvious, I'll just let you write a few terms out. Take this list of steps and look through the previous problem and see that those were indeed the steps we did, and see how to apply them to the problem. Here's another problem. Try this one. Apply the same sequence of steps that we did in the previous problem. This one's a little bit more tricky. There are 2 inputs, and now the latest output in time is this term with an n plus 1. That's later in time than n is. Keep track of what your n's are, and keep track of what your h of n's are. They are shifted by 1. Pause the video, do the calculations. When you're done with the calculations, sketch your function. Here's all the answers. Solving for your latest h of n. Get this equation. Initial rest condition. Write a few steps out. Fast forward. H of 0 for this one is still 0. When n is 0, our equation is h of 1 equals delta of 0 minus 2 delta of negative 2 minus 3h of 0. That's why h of 0 is 0, but our h of 1 is where we have things actually turn on. It's when n is 0, but our h value is 1. And then we iterate forward. And that's what it looks like.